Hello, everyone, and welcome to today's graph reading group.
Where we're joined by Andy and Farimah presenting their work on dynamic link prediction and explaining us what this field is about. Let's go.
So hello, everyone. So my name is Huang, or you can just call me Andy. Today I will be presenting along with Farimah our recent work accepted to the NeurIPS 2022 datasets and benchmarks track. And as a quick word on me, I'm a PhD student at McGill and Mila, and I work with Professor Rahani Rabadi and Gelong Barbusu at Mila. And my main research focus is on learning from temporal graphs as well as anomaly detection in temporal graphs. And and I have a co-presenter, Farimah, today. Maybe before we get started, we can take just very quickly. Do you want to introduce yourself, Farimah?
Yes, hello everyone. I'm Farimah. I'm a new postdoc in Rehana's group. My major interest in research is learning on temporal graph. And during my PhD, I work on a similar project like learning on temporal graphs, but for node classification and anomaly detection. And I will present the second part of the slides today.
All right, sounds good. Thanks, Farimah. So as Hannah's mentioned, so we have shared the link to the slides in the Slack, and so you can follow the links there to see more. And today I will be presenting towards better evaluation for dynamic link prediction, and I will be first giving an overview. I think down this back. I will be first giving an overview for the introduction, as general introduction to dynamic or temporal graph learning. So for the context of this talk, we use these two these two terminology, temporal graph and dynamic graph, interchangeably. And in general, in the literature, they are quite interchangeable. And I will be discussing first are what are the formulations for dynamic graphs and what are different types of dynamic graphs. And then I will be discussing the tasks on dynamic graphs. And then for the interest of time, I won't be going into the specifics of particular methods, but I will be giving references and example methods for different categories of tasks. And then you can follow them on the slide. And then for the second part for the talk, we'll be focusing on the dynamic link prediction problem. And then Farimah will be covering our paper, which aims to improve the current evaluation setup for dynamic link prediction. Okay, so I will get started here, and then feel free to stop me if you have any questions. Okay. So first, as a I was very quick introduction. And I think most audiences are familiar with networks. So here are two example networks, and we have basically different nodes, and then they would have relations between them. So one example network we have on the left is the Canadian Bill voting network. So this actually models the co-voting behavior of members of parliament in the Canadian parliament. And this is one example network. And then for the second type of network, you can also have the social network. So here I'm showing the University of California Irvine social network. And this is also a classical dynamic graph network. So as we have these networks, the informations and the edges in the network can actually change significantly over time. And shows different relations, which is the focus of temporal graph learning and dynamic graph learning. And first, just very quick notation. So when you have a static graph, you have a static graph consists of a set of vertices and edges, where the vertices can be labeled from 1 to n, and the edges can denote the edges between all the relations between a set of nodes. And you can also have node and edge attributes. as a visual example, here is one snapshot, which is simply a static graph from the Canadian Parliament network that I mentioned before. And this is from 2012. And the color here can be considered as node attributes. These are the party affiliation. The nodes are the members of parliament, and the edges means they have both voted yes on the bill. So that shows the positive social relations between them. So now getting to the temporal graph part. So how do we model an evolving network? So in the most general sense, we have two categories of dynamic graphs. So here the first category is called discrete time dynamic graph. So these are dynamic graph structure most suited when you want to model relations that are sampled or collected at regularly spaced intervals. And then you have the different type, which is called continuous time dynamic graph. This is more general, and this models the interactions at irregular or continuous time intervals. So the edges can arrive at any time. While in the discrete time dynamic graph, like the edges will be like arriving at fixed and equally spaced time intervals. So I will first define the discrete time dynamic graph. So you can consider discrete time dynamic graph as an ordered sequence of static graph snapshot. So you take the static graph formulation that we have from before, and then essentially now you have an ordered sequence of them. And then the time that had been passed between each like static graph snapshot is equally spaced in this case. So when you have the discrete time dynamic graph, you would usually have like political interaction networks, because political events are usually released on an annual basis, for example. You can have international trade networks. So these would be like understanding the relations between like different nations. And these are like also usually like released annually. And then you can also have citation networks. So these will be examples for discrete time dynamic graph. So going back to the earlier examples, now we have the full like one set of visualization for the Canadian Parliament voting network. So you can see that at different snapshots, the graph structures will change, and you can also have different kind of behaviors. But in general, like we consider that there are some like some consistencies between the snapshots, but some external events or changes can cause a change in the graph structure as time goes on. And then for the second type of dynamic graph, which will be the like the focus for our paper as well, is continuous time dynamic graph. So a continuous time dynamic graph can be considered as a pair of the initial state of dynamic graph. So the G0, which tells you of the initial node and edges you have at time equal to 0, and then a sequence of observations. So these observations can be very general. So this can have an event type, as well as what the event is, as well as the timestamp of it. So by taking the initial state of your dynamic graph and then sequentially applying the sequence of observations you have, then you can obtain a graph snapshot or a graph structure fixed at time t. And here we consider t to be equal to the initial timestamp 0. And then examples of the continuous time dynamic graph can be social networks. So like the messages between users and interactions can happen at any time, as well as traffic networks and many, many more. And then in terms of the evolutions you can have in dynamic graph, or the set of observations or the events and changes you can have node addition and deletion. You can also have the edge addition and deletion, as well as you can have node and edge attribute change. Depending on the task of interest, you might be focusing on any of these entities. Now we have the formulation for dynamic graphs. Now we can look at what are some standard prediction problems from the literature that people apply and learn from dynamic graphs. So you can have the standard set of tasks such as link prediction. You can also have node and edge classification. You can even have graph classification to classify different types of temporal graph, as well as a very application-focused type of anomaly detection. I will be going over the link prediction, node classification, and anomaly detection formulation for today. And then in terms of reasoning on dynamic graphs, you can actually have two types. So one is the interpolation, where you're given some data, but you might want to label some things in the past. You can also have extrapolation, which is looking at events happening in the future, and that's the most common type of task. So given the information up until time equals to t, you want to model the relations, the edges, or the nodes that you have after time t. Okay, so here is the dynamic node classification, so which will be the first task that I discussed. So similar to the standard node classification, the key differences here is that we have a timestamp information in the query. So given a discrete time or continuous time dynamic graph and a query of the node of interest u as well as t prime. So you can actually have t point be any time point, but for the most cases you want to predict events in the future. So you have t point bigger than t. And the objective is to predict the class of the node u. You can also have like node regression as well. So here, like I did a simple illustration about like what I mean. So you have information of the node labels from t equal to 0 and t equals to 1, and you want to know how the labels or the nodes have changed in t equals to 2, given the graph structure. And then here are some example methods for dynamic node classification. And yeah, so I'll be going to the methods for detail for today, for the sake of time. And then for the background, now I want to talk about the anomaly detection task for graphs. And for those who are not familiar with anomaly detection, I'll be going over like very quick background on what it is. So basically, given a graph, you can find anomalous node edges or subgraphs that are different or deviate significantly from what you have observed in the graph. You can consider them as anomalous users or anomalous activities and so on. And in general, the approach is to design an anomalies like scoring function of fa of x, which usually lies between 0 and 1, and you have the 0 case to be more normal and the 1 case to be more abnormal. And the key differences here of anomaly detection is that in general, you don't have a lot of supervised signal because it's difficult to obtain labels for anomaly. And also, you have very extreme class imbalance. So you can consider anomaly detection as a binary classification where you are labeling some entities as normal and some entities as abnormal. But usually, the abnormal entities are assumed to be 1% versus 99%. So you have very extreme class imbalance here. So this is usually treated as an unsupervised task due to the above reasons. Okay. So now you can extend anomaly detection to dynamic graphs. So now given a discrete time or continuous time dynamic graph, you can find anomalous node, edges, subgraphs, as well as entire graph snapshot. So the entire graph structure at particular points can be different. And here to list some example applications, you can do bot detection in social networks, as well as email spam detection, traffic accident identification, as well as change detection in political environment. So So as an examples, like we see that on the right, we have two communities, 1 and 2. And then from time step 1 to 2, the node 6 have now been involved in both communities, as opposed to just one of them before. So this could be one example of anomalous behavior that you want to model. Okay, and here I will cover some example methods as well. So feel free to go through the reference if you're interested. And then in terms of my work, I've been mostly working with anomalous snapshot detection. So trying to model the change in the graph distribution over time in a temporal graph. And I listed one of my my previous work here in lab, like at the bottom. And now we're going to the task of the task of interest and focus for today, which is dynamic link prediction. So in this case, we are once we have a dynamic graph, then we have a query of u, v, and t prime. So t prime is the time you want to know if a link exists or not, and uv is the node pair you want to test on. And the goal is you want to predict the probability of an edge existing between node u and v at future time t prime. And again, I have shown an example here. So given the information from t equals to 0 and t equals to 1, we want to predict the links at, between AD and BD at t equals to 2. And then here are more example methods in the from the literature. Okay. So to to summarize on the background in learning from dynamic graph, we have a few significant challenges in learning from dynamic graph. So the scalability problem already applies in static graph, but in dynamic graph it's even more challenging because at each day you can have millions of edges coming in at each day, and you want to process them in a timely fashion. So you want to be able to scale to millions of edges, as well as ideally in an online fashion. And you also have temporal reasoning. So given the complex dependency of edges in the graph, you want to not only model it from the graph snapshot that you have currently, but also from the previous temporal dependencies. So you can have your current edge or node behavior dependent on many snapshots in the past. And another challenge that we'll be trying to address in our paper is the evaluation protocols. So sometimes when you just take the static graph evaluation protocol and bring it to dynamic graph, it might not be the best way to do it. So you want to consider the temporal information as well as the overall structure of the dynamic graph when you are designing evaluation protocols. And then lastly, you have the lack of labels. So this is more severe for when you for when you want to do node classification, because it's difficult to attain labels for each of the time, as well as for anomaly detection. So as an example here, you have a New York City taxi dataset, and I show the visualization as follows. And some example questions you can ask is that, how do we predict the edges in the next snapshot? So that will be dynamic link prediction. And then how do we detect change in the node behavior? So this can be framed as either node classification or node regression. Okay, so that covers the background for dynamic graph learning. Is there any questions? Yeah, and also if you want to learn more, we are also co-organizing the temporal graph learning workshop at NeurIPS 2022. And this will be an in-person workshop, but also it has it will be streamed online as well. So if you want to find out more, feel free to join the workshop. And I provide the links to the Twitter and the webpage here. Okay, so if there are no question, yeah, I will be forwarding the torch to Farimah. like to cover the second part of the presentation. Now we have the background on dynamic. Do you want to share your slide, Farimah?
Yeah, thank you, Andy, for covering. Now I can share. Can you see the slides?
Yep, perfect.
Okay. Okay. At this point, I will go over our paper, which is titled "Towards Better Evaluation for Dynamic Link Prediction." We have actually roughly summarized the current evaluation setup for dynamic link prediction. In this type of task, there is a temporal split of the data. It means that we have a data set and we chronologically split it into train, validation, and test set part. In most of the different tasks, we can see that the dynamic link prediction is modeled as a binary classification. So we need a set of positive and negative instances. The positive instances are the actual edges that are given in the data set, and the negative edges should be selected by some criteria, which most of the time we see that they are randomly sampled from all possible pair of nodes. And the metrics that are mostly used are AURC and average precision. And finally, one interesting observation is that the performance of the link prediction task for most of the currently state-of-the-art models are significantly high, and in some cases it is close to perfect performance, which is one motivation for us to evaluate the settings that these models are being investigated. With that overview of the link prediction evaluation setup, we started by looking at the currently available data set. We understand that the data set that are used for dynamic graph learning, they are mostly from some limited domains. Most of the data sets comes from social networks like Wikipedia and Reddit that are much used in many of the dynamic graph learning problems. And apart from being limited in the domain diversity, we can see that most of the state-of-the-art methods can achieve high performance. For example, more than 94% AURC in link prediction in Wikipedia and Reddit dataset. So it was a motivation for us to see what is the fact behind them and whether the evaluation setup is powerful in performance evaluation on this task or not. So as a summary, we have three main contributions. We propose new data sets that can increase the diversity of the domain for dynamic graph data sets. And we also had some new visualization technique that help us to better understand the attributes of the dynamic graphs. From another point of view, we focus on the importance of negative sampling for the evaluation of the link prediction models. And we propose two negative sampling strategy there. And finally, we propose a simple but a strong baseline for dynamic link prediction. And I will go over each of these contributions in the same order that I have in this slide. So let's start from the dataset investigation. The dataset that we have proposed, they come from some domains that have been less or unexplored. For example, transport, politics, and economics. And we actually wanted to increase the domain diversity because if we increase the domain diversity, then we have diverse properties and we have different graph distribution. So it will help us to have a better evaluation setup for different models. And as we can see here, different graphs like the cycle, complete, or line graphs, they have different properties. So it is good to increase the domain diversity. In order to have a better understanding of the dynamic graph datasets, as I mentioned, we have two visualization techniques that help us to better understand the statistics of or attributes of these datasets. But before going to introducing the visualization technique, I want to briefly talk about the edge types in dynamic graphs. So if we consider that we have a split of the data set into train and test set by a time of test split, then the edges can be divided into three main categories. First, we have some edges that we can only see during the training. Then we can have some edges that we see during the training, and due to the reoccurrence pattern of the dynamic graphs, they can reappear over the test, and we can consider them as transductive edges. And finally, we can have some edges that we only see them during the test, and we can consider them as inductive edges. So having these categories of the edges in dynamic graph, we first have one visualization technique, which we call it T-plots. They show the temporal edge appearance plot, and specifically they show the repeated versus new edges at each of the timestamp that we look at the network. So here we have the T-plot for the Reddit dataset. In the next slide, I show the T-plot for other dataset, and there we can see that there is a high variance in temporal evolutionary pattern. Based on these plots, we have defined an index, which we call it novelty, and it shows the average ratio of the edges that are new at each of the timestamp to the total number of edges that we see at each timestamp. And this metric, it gives us an estimation of the portion of the positive edges that a pure memorization-based approach can predict correctly. So here you see the T-plots for the remaining data sets with the novelty index specified in the parentheses under each data set. So we see that there is a diversity in the novelty and also in T-plots of different data sets. And some data set like Wikipedia and Reddit that came from similar domain like social networks, they show similar behavior in their T-plots. And also we can see that some data set like the social evolve, they have many repeated edges, while the other data set like the mark, it shows that they have a lot of new edges. Also, we can see that there is a significant difference between the data set from different domains and the ones that we have proposed, like the flight data set. It has a higher number of edges at each timestamp, and also it shows that there is distinction between the new data set and the currently available data set. So it's also important to consider the ratio of the repeated and the new edges when we want to design a new model. There are many information that we can get from these plots, but one thing that we cannot see here is that how the edges will reoccur over time. And that's where the TED plot or temporal edge traffic plots come into the play. Here we show that we show the recurrence pattern of the edges over time. Here we have the TED plot for the Reddit dataset. On the x-axis, we have the percentages of the observed edges, and the time axis we have the on the y-axis we have the timestamp that the edges have been observed. The green bars actually they show the edges that we only see during the training. The orange ones show the transductive edges that we see during the training, and also they reappear over test phase. And the red ones they show the inductive edges that we only see during the test phase. And based on these plots, we also define two different indices, reoccurrence and surprise. The reoccurrence shows the ratio of the edges that we see during the test and training to the total number of training edges. And the surprise, it shows the ratio of the edges that we only see during the training we only see during the test to the total number of edges during the test. So here we have the TED plot for the remaining data set with the reoccurrence and surprise indices specified in the parentheses. So these plots actually they provide some insight about the edges that we can see during the training or test for different models, and they also imply some important information. For example, if the edges reoccur over time frequently, that is the case where reoccurrence pattern is high, then a simple memorization-based approach can achieve good performance. And on the other hand, if there are some data set that have low performance, like mark, then a simple memorization approach will not work very efficiently. And on the other hand, if there is a data set which has a high surprise, then we can see that a memorization approach is not helpful because those edges are new and they haven't been saved in the memory. Actually, these T and TET plot, they show the importance of the edges that we select for the evaluation of the link prediction models. And considering that in the edges that we select for the evaluation, we have two different sets of edges. We have a positive and negative edges. And here we want to show that the negative edges that we use for the evaluation of the methods are as important as positive edges. So I will go back to the notion that we saw that in many of the link prediction models, the task is modeled as a binary classification problem. But the problem is that we have only the positive edges that are the actual edges of the network. And we need to select the negative edges according to some criteria for training or evaluation of the models. And the current evaluation setup is that we randomly select the negative edges from all possible pair of nodes. But one of the problems with this strategy is that although it may sound feasible for the static case, but for the dynamic case, it has a major problem because it doesn't consider the recurring pattern of the edges. With that in mind, we have proposed two different negative sampling strategies. The first one is the historical negative sampling strategies, where we focused on the fact that the edges reoccur over time. So the negative sampling should be aware of the recurrence pattern of the edges. So here we select the negative samples for the evaluation of the models from the observed edges that we have seen during the history of the network, but they are absent in the current timestamp. For example, here we can see that we select the negative samples from the training edges that we don't see them during the test set. The other negative sampling that we have proposed is the inductive negative sampling. Here we have focused on providing more negatives, harder negative samples from the set of edges that we have seen during the test, but they are not reappearing or they are not reoccurring over the next timestamp of the test phase. So the sampling strategy consists of edges that have been observed during the previous timestamp of the test phase, but they are absent in the current timestamp. Apart from the sampling strategy, I also mentioned that here we have the impact of negative sampling. We show that with different negative sampling, we can achieve different performance. For example, if we go from this standard setting to the historical or inductive setting, we can see a considerable performance drop in the performance of the different models. And it shows that this is important to evaluate the methods with different negative sampling strategies. And also we see that the ranking of the methods will change if we use a different set of edges. As I mentioned during the introduction to the T and TET plot, I mentioned that if we use this memorization approach, that will help us to achieve some good performance for at least reoccurring transductive edges. So based on the observation from the T and TET plot, we saw that many edges reoccur over time. And we were thinking that whether the memorization approach can work well in this area or not. And for that, we proposed the EdgeBank, which is a pure memorization approach. And we have an illustration of it on the right. For example, here we have considered that EdgeBank is a bank of edges, that if we observe one edge, we can save it in the memory and answer the link prediction question based on what we have saved in the memory. For example, we have for the query one, we have these edges in the memory, and the link prediction task will return true. And for query two, because we don't have this edge in the memory, then we will predict the probability of these edges as false. So EdgeBank, which is a simple baseline, it is very helpful for the edges with the frequent recurrence pattern, but in two cases it fails. The first case is when we want to answer the link prediction task for a negative edge that we have seen before. So we have it saved in the memory, but it is absent in the current timestamp. which is comparable to the historical negative sampling setting. And the second scenario where EdgeBank fail is for the unseen positive edges or unseen inductive edges because we haven't saved them in the memory. So we also have two different variations for memory update policy for the EdgeBank, namely EdgeBank Infinity and EdgeBank TW. In the EdgeBank Infinity, we store all of the observed edges in the memory, so it remembers edges from a long time ago, but it is prone to false positive, because if one edge has been seen before, but it is not reoccurring, then it will falsely return 1 for the link prediction task. And on the other hand, we have the EdgeBank TW, which remembers edges only from a fixed time domain from the immediate past. And we have set the duration of this time window equal to the duration of the validation split. And this strategy focuses on the edges seen in the short-term past. And here you can see the EdgeBank performance with the different negative sampling setting. One interesting observation is that it can achieve competitive performance, particularly in a standard setting, and EdgeBank TW can achieve a high performance in a historical setting. And it can be among the state-of-the-art in this setting. So right now I will go to the experimental results. The model that we consider for our evaluation are as follows, where CW and TGN are among the state-of-the-art methods for dynamic link prediction. First, we have the results of the dynamic link prediction task in the random negative sampling setting. We can see that there is an inconsistency in the ranking among methods across different data sets. There's not just one method that can have the best performance in all of the different data set, and that shows the importance of increasing the diversity of the domain and having more data set for dynamic link prediction tasks. And here we can see that our new data set, they have different rankings for different models. And the other observation that we can have is that the memorization-based approach, they can have on-par performance with the state-of-the-art in many of the data sets. Then we have the results for the dynamic link prediction when we use historical negative sampling. Here we can see that the EdgeBank TW is among the state-of-the-art in many data sets, and it shows its performance. It's very important to update the memory with the more recent, with the edges that have been seen more recently. And the other observation is that EdgeBank Infinity does not reach good performance because it doesn't update the memory. And finally, we have the inductive negative sampling setting, where we don't expect the EdgeBank to work well because inductive edges are the edges that makes the most problem with the EdgeBank. And one other interesting characteristic is that we saw that the recurrence index for the mock dataset is very low, so we see that the performance drop in the inductive setting is also significant. And here we show that the impact of negative sampling across all of the methods. We can see a clear gap, clear drop in performance between different negative sampling, which is compared to the standard random negative sampling. And also it again shows that the ranking of the models will change when we use different set of edges for the evaluation setup. And finally, we showed that there is a correlation between the performance of the EdgeBank Infinity and each method in the standard setting and the performance drop in the historical or inductive sampling setting. So if we have a higher correlation with the EdgeBank Infinity, then we can expect to see a higher performance dropped when we use harder negative samples. So in conclusion, in this paper, we were focusing on the dynamic link prediction task, and we want to have a better evaluation setup for the dynamic link prediction. And in this regard, we proposed 3 new domains with 6 new datasets and visualization techniques that help us to better investigate the characteristic of the dynamic graph dataset. We focus on the negative sampling and its importance in evaluation of the different models, and we propose historical and inductive negative sampling. And we show that the method ranking changes when different negative sampling are tested, and both settings, meaning historical and inductive, provide more difficult negative edges. And finally, we propose a simple yet powerful baseline, which was purely based on memorization, and it shows how different methods can go beyond the memorization. Thank you very much for listening. And here are some resources, and we will be happy if you find it interesting, and you can reach out to us.
Yeah, thanks for the presentation and for setting up this library and for the paper. Yeah. Do we have any questions?
Yeah, so I have a few questions, but first I'd like to say thank you, and I really like the work that you've done. It helps, like, how to say, put more sense into the work that is being done in dynamic graphs, because when you look at what Andy and yourself were mentioning, that OROC scores of 94 and 95, they don't really allow you to see what's working, what's not working. And by introducing these new concepts, it really helps better, like, see how the graph, the method for dynamic graph perform actually in real world setting, especially like studying them on different sampling. One of the questions that I have here is you've defined. I really like the definition of reoccurrence and surprise that was presented earlier, and I was wondering if, like, these could be used instead of using different sampling strategies. Use metrics based on reoccurrence and surprise instead of resampling. What do you think about that?
First, thanks for your interest in this work. And right now we have actually more qualitatively show that there is some correlation between these metrics and the characteristic of the data sets. We haven't looked at the exact correlation between the way that we can sample the edges of the negative sampling and these data sets, but definitely there is some room. I mean, because we saw that, for example, if some data set can have like the mark, it has a very low reoccurrence, and then the performance drop in the inductive setting is very high. So definitely there is a correlation between these observations, but we haven't yet formalized it. So it is more, I mean, at this stage, it is more like looking at the data set and compare them, and then we are trying to define some way of using these metrics in the negative sampling strategy, or even to improve the EdgeBank, so that it can be somehow aware of the different characteristics of the data set based on these indices that we have defined.
Yeah, thanks. So just to make sure I understand, EdgeBank is not a machine learning model. It's really like about memorization and repeating what it has memorized, right?
Yeah. Exactly.
And why? So my original question is more like, why go for resampling methods for the test set instead of trying to measure what's the accuracy or the OROC when an element is new versus when an element is not new? So, for example, having accuracy for surprise and accuracy for reoccurrence, and have these two metrics being used in parallel.
Yeah, actually, that's a very good point. I can say that we thought about it, but we haven't tested that yet. But yeah, I mean, in some sense, we were thinking about looking at the different set of edges. I mean, like separately, for example, looking at the positive and negative edges separately. But yeah, this is a nice addition to look at the importance of these metrics and then the final performance of the method.
Yeah, thank you. Also, Yeah, something I think I misunderstood, for example, from the presentation. When you do the negative sampling, like how do you split the training and test set? That's something I didn't really understand because the temporal graph, usually the training set is the first few days, and then the next few days are the test set. When you do this kind of new sampling, like, can you explain a bit more details how the train and test set are being?
Yes, actually, as you mentioned, the split of the data is based on the temporal observation. But in the current evaluation setup, the negative samples are randomly selected from all possible pair of nodes. So they don't consider any temporal information. They just consider that, for example, we have a fully connected graph and we can sample any nodes. And we can sample any pair of nodes and we can consider it as a negative edge. But what we have done is that we focus more on the edges that we have seen, for example, in the historical setting. If I go back here, we focus more on the historical setting that we had, and we sample the negative edges from the edges that we have seen during the training, but they're absent during the test. For example, we try to sample edges from randomly from the edges that are green here. So instead of randomly sampling from a fully connected graph here, we sample from the green edges that they don't reappear at the test time.
Right. So if I understand, like during the when you're working at a certain time t that is in the test set, it means that you sample part of the edges. You don't kind of try to make predictions everywhere. You have already some labels and you try to predict missing labels, or
exactly. Yeah.
Yeah. Okay.
Yeah.
Okay, I think that's the part that was a bit confusing to me. So you're never trying to predict the entirety of the graph at every step. You predict some.
No. Okay. Yeah, for the positive edges we have them, and for the negative edges we just sample some subset of the edges for evaluation.
And I think one of the cool possibilities would be to see how you could mix EdgeBank with a learned model, like, for example, a hybrid machine learning model with a memory model, to see how the network can also like modify, like not necessarily use its memory directly, but assess whether it should use its memory or try to predict something new. I think that's a very good set of work that you've done, a very great baseline into like studying dynamic graphs. And thanks a lot for your presentation.
Thank you very much for the feedback.
Andy, I see that you're answering a lot of questions in the chat. So if you'd like to let the audience know what is being discussed in the chat, so that everyone can, so everyone can have an idea of a few more questions.
Right. So I think the question from the chat from Shirin is like, sorry if I pronounce your name like incorrectly. It's about how to construct temporal graphs from tabular data. And actually, this is a very interesting direction in how to convert different types of complex relations you have, let's say with timestamp information, into a temporal graph. And currently, we mostly have like a lot of the graph domains, as in like social networks and so on. And it's quite straightforward. But actually, when you have this type of complex biological data sets and so on, like this might require a bit of like thinking depending on the nature of the edge you have. What are the nodes? And then what is the best way to understand like the changing relations between them? So maybe, yeah, so I can read the, but I think this is more like suited for like in-depth discussion later. But I think the data is based on a set of like immune cells and So I'm just reading the question, and these blood samples are collected at multiple time points, and the cells are associated with each other based on some of their features, and how do they combine the data from multiple time points. So yeah, so I think depending on the nature of the data, I think like maybe you want to understand how does the like the evolution of the relations between the nodes can happen, and this is usually where like the construction of a dynamic graph is more helpful, because if you collapse everything to a static graph, and then sometimes that's what you want to do, but you lose the information about how does the edges change from one time to another, and sometimes that's what you want to model. So I think it depends on if you want to understand that from the process. Yeah, and you can actually frame like different problems in this way. So like in the paper, I just want to just kind of briefly discuss is that, so the new data sets that we proposed are from interesting domains such as politics. So in the politics, the edges are kind of different. Yeah, so this slide is perfect. Thanks, Farimah. So like for for politics, usually the interactions are very different from the social media kind of data set, because you have a usually fixed set of nodes. You have this many number of parliament, and it's not going to change that much or like ever. But the interactions between them are changing, and this graph can be very densely connected because you have a lot of votes that requires many of the members to vote yes to be able to pass. So the distribution here is more closer to a fully connected graph than the sparse graph that we observe in standard social networks. And also one of the motivating data set that we have to design the historical negative sampling is the flight network. So this data set is particularly interesting because when you are looking at flights, you actually don't care that much about if tomorrow there's a flight between Toronto and say the North Pole. So very, very little application will be focused on that. What you care about is how are the flights going to change between destination and a source and destination that you already know. So like if you have the flights between Toronto and Montreal for the past week, how do you predict the flights for like between these two destinations for the next week? So that's why like the historical negative sampling is much more important in this data set. And like if you just look at the randomly sampled negative edges, it will do really well. So if you can go to the actual performance on the random one, so like on the random one, the flight is actually close to 100% AUROC or above 90% for most of the data set. If you randomly sample the node pair. So that's like asking the question, okay, I have a flight for tomorrow between North Pole and South Pole. So it doesn't make too much sense. But if you go to the historical one, you can actually see, so actually the drop in performance plot. I think you were showing that like earlier, Farimah. I think it's later on in the slide.
Sorry.
So that one, yeah. So you can see this has the most drop in performance from the standard to the historical one, as well as inductive. So this means that it's really, really difficult to actually like specify these these flights. And the AUROC here is actually around like 60%. So if you random guess, it's 50% like AUROC. So it's not that much better. And the reasoning here is because this particular data set is actually from January 1st, 2020 to around April or March in 2020. And that's actually where, so in the middle of around the test split is where the COVID events happen. And you have travel restrictions. So you have you actually have one example of distribution shift here in the data set in temporal graph. And that kind of changes how the performance play as well. So I think here, in this work, we will try to understand how can we design the evaluation procedure more closer to the application for temporal graph, and also there's a lot more room for future methods to improve, based on the historical and the inductive setting. So just just kind of follow up on discussion from before.
So now we actually have a good benchmark for dynamic link prediction, but so we need people to use it. So go ahead, use it, and write your papers. See you.